Next week, class will meet, but you'll have an exam. Dr. Halazinski will give you the exam. Given the content of the exam, there will be some computer material on it, but he'll also provide you with the lab laptops and a printer that you can use to print things out. The material on the exam, UV or spectroscopy and electrochemistry. And you got the review sheet last week when you were here. I think you all have it now. I'm not sure, but if I can manage sometime in the next couple of days, I'll try to write out a key for it. I make no guarantees right now, unfortunately. There's just too much going on. But I'm leaving tomorrow afternoon, and if all goes to plan, I will be back next Wednesday, and I might actually get back right around the time that you're working on your exam. If not, and there's a distinct possibility that I might have to stay longer. So keep your eyes open. Look at the announcements in Canvas. If I end up missing lab, somebody will definitely cover for that. It's just class that I'm more concerned about. How am I going to figure that out? But I've got everything I need to put together a video for the next material if need be. So what we're going to do in this part of the class is this is the last unit of the class. And we're going to focus on separation of mixtures. We're going to talk about things in very general terms. And then we're going to get into some specifics and really focus on the specifics for the remainder of the semester, okay? And the thing you want to think about is really, at this point, we have 3 more lecture periods after this one, okay? We have an exam next week, the following week, and actually really 2 more weeks. And then you're going to have your last exam, you have your final projects. That's one of the things you really want to spend some time on next week as well, is starting to get an idea together for an independent project. There is a list of independent projects under the lab section of the modules up near the top of Canvas. Take a look at it. Start thinking about things. If you want to email me or text me or even call me about those things, if you try to call, just give me a heads up about it, all right? I can take calls, but it may not be as convenient excuse me, as it would otherwise, because I'm going to be doing a whole bunch of things as well. But if you want to talk to me about something, we can set up a time when I can talk to you. All right. And the other thing that is true that we may have to utilize, depending on how long I end up having to spend out there, is Canvas has a conferencing tool. And so if you can use the video camera on your computer to call in a conference if need be. Hopefully it won't come to having to use that, but I don't know what the future is going to hold me right now. And if I'm listening to the things that are coming down the wires right now, I'm a little concerned about what's going to happen in the next few weeks regarding my sister. So we'll see. All right, so separation of mixtures. A very, very broad-based topic. Am I correct that you all either have had organic chemistry or you're taking organic chemistry now? Is that true? I know you're taking organic chemistry, Justin. Oh, you finished? Okay. All right. For some reason, I thought you had Dr. Levy this semester. Okay. And Glenn, you're taking it? Okay. And Santiago? Okay. Very good. So why would you want to separate a mixture in that context? Why would you want to do it? Yeah. Okay, that's probably the most common application of separations of mixtures as a whole. Is somehow you need to purify a product from a reaction mixture. And that's essentially what organic chemists look at when they do separation of mixtures. Analytical chemists tend to look at quantification more than purification as a means from separation of mixtures, although the two are not really that far apart. Especially if you get into areas like process where you're trying to make, say, a drug, and you want to maximize the yield that you get from an industrial process just because it becomes much more cost effective, then you have to think about the analytical side of things as well. But on top of that, from a perspective of analytical chemistry, the whole principle of separation of mixtures is one of the ways that drug companies check the quality of their products. And we had, for a long time, we had a chemist here by the name of Dr. Yarmchuk who did that during his career in industry before he went into teaching. He was working with Novartis trying to figure out quality assurance. You know, basically, they had to prove that the compounds they were making were what they said they were. And that's one of the things about pharmaceuticals that you trust, but I'm not so sure you always should. Okay, this is one of the problems I think with generic medications that we haven't addressed so well in this country, is that a lot of them are not subjected to the same quality assurance that name brand products are. And as a result, sometimes you're not always sure what you're getting. All right, get ahead of myself though. So, what kinds of purification techniques are there? And that's essentially what we're going to talk about mostly today, is kind of an overview of purification techniques, and then a technique that probably at least some of you have done in organic chemistry. There's the first one. Say, for example, you have a reaction mixture. You isolate a crude product from the reaction mixture. One of the ways you can clean up that product is by recrystallization. And there are a whole bunch of different ways to do this. The inclination of organic chemists is to dissolve a minimum amount of your crude mixture into a hot solvent and then cool it down. And I think that's one of the labs that's at least one of the labs that's done in Chem 226. But there are other ways of doing this, and I learned these as an inorganic chemist. One of the other things you can do, which isn't as lean on the solvent, but sometimes is necessary, if you have a compound that can't withstand heating, one of the other things you can do is dissolve it in a minimum of a solvent that it goes into, and then what you can do is add a second solvent that your compound is not as soluble in, and get it to drop out that way as clean crystals. And I used this extensively as a graduate student to clean up products that I made. And also, another reason to do it this way is that you can grow crystals that are of high enough quality to get an X-ray structure, which is what I did. And it's really a nice way of doing that. So, we can clean things up by recrystallization. If we have a mixture of liquids, we can clean things up by distillation. And probably the way this is used the most is to purify alcohol. For those of you who've done the GC lab, what you're looking at is distilled spirits, and you're trying to determine the quantity of alcohol in a distilled spirit by volume based on GC. Okay, so the idea of distillation is to purify based on the difference in boiling points. The other place this is used very heavily is in petroleum products. All the different petroleum products, gasoline, diesel fuel, jet fuel, natural gas, they're all a result of taking crude oil and distilling it and collecting specific fractions. Gasoline is a very specific fraction. It has a narrow boiling range, and that's and essentially the distillate that comes over a distillation in that boiling range is collected and then sold as gasoline. Although oftentimes refineries will add a few things to it as well, such as ethanol to boost the octane rating. All right, so there we go. Again, something else you've done in organic chemistry. You have a reaction mixture and you want to clean the reaction, you want to clean certain things out of the reaction mixture, you can do what's called the liquid-liquid extraction. You have two solvents that are immiscible with each other, say, for example, water and hexane. Your organic compound stays in hexane, but there are some byproducts of the reaction that you need to wash out that are water soluble, and so you wash with water. And this is probably the main area where this is done, is certain types of organic synthesis. I don't think I've seen a liquid-liquid extraction done outside of an organic chemistry lab ever. I worked in industry for a while, and everybody just used chromatography as a way of extracting, mostly HPLC. Anyway, there are several ways that we can calculate what goes on within a liquid-liquid extraction. One is called the distribution coefficient that focuses on weight. What analytical chemists are much more inclined to look at is what's called the partition coefficient, where instead of having weight over volume, you have moles over volume. And so we use partition coefficients to show molarity of whatever's in the extract over molarity in the original solvent. And so this is, this is used. Actually, when I took this course when I was an undergraduate, we actually determined a distribution coefficient for water and carbon tetrachloride and bromine. You took a solution of bromine, you washed it with water, and then you determined the amount of bromine that was in the water layer. And we calculated the partition coefficient. So one of the reasons I bring this up is I wanted to show you something. When you did separations in organic chemistry, in other words, when you used a separatory funnel, how many times did you wash? Yeah, exactly. Why do you wash 3 times? And you could also ask the same question, because the principles are very similar. Why do you rinse glassware 3 times with a solution before you fill it up? It's kind of the same principle. All right, so let's do a very simple calculation with this. We have a particular solute, and the partition coefficient between chloroform, which is organic based, and water is 10. Okay, and so if we start out with 100 milliliters of a 1 molar solution, a 1 molar aqueous solution, let's put that in here. If I start with 100 milliliters of 1 molar aqueous solution, and I wash it with the same volume of chloroform, what happens? Okay, here's what you can say. The distribution coefficient is 10. Okay, the amount, or the 10 pertains to the molarity of the solute in the chloroform. We'll just call it A. And chloroform is CHCl3. Divided by the molarity of the analyte in water. Okay, now how do we figure those things out? Well, we know the initial molarity of the analyte in water. It's 1. In this equation, this is going to be that 1 molar minus some value x. And on the top, we're going to have x molar. And so we can plug that in. We can say, all right, 10 is equal to x divided by 1.0 minus x. Multiply both sides by 1.0 minus x. We get 10 minus 10x is equal to x. And so x, let's see, 10 is going to be equal to 11x. And so what's x going to be equal to? What's 10 divided by 11? Is it 0.999? No, it's got to be, oh, 0.909? Okay. So, essentially what you can say is by this calculation, we've washed out 90% of our solute. Okay, by using an equal volume of our organic solvent with our water, we've washed out 90% of our solute. Okay, now, what about in this next case? What if we wash with successive 15 milliliter portions? How much are we going to wash away? Again, we're going to get the same thing. 10 is equal to x divided by 0.1, not by 0.1, 1.0 minus x. We're going to do that 3 successive times. How much are we going to get out? A whole lot more. And we're going to use a lot less solvent. Okay, we're going to take out fewer moles each time from the aqueous layer, but we still get the same distribution coefficient, and so therefore we're going to take out a whole bunch more solute than we did previously. And because of that, it makes a difference. All right, so smaller washings do a much more effective job. It comes up to be 99% in this particular case, or 99.99% if you go all the way through with it. All right, but it's the same basic thing. And so you're going to see on this next homework a couple of problems that deal with distribution coefficients. And I would strongly recommend too that you read the section of the book that goes through some of the calculations, because it has some very complex calculations that you can do with these distribution coefficients and also with the partition coefficients. Actually, I'm sorry, this is a partition coefficient. I always get that mixed up. They're basically the same thing. The only difference is a distribution coefficient deals with mass, a partition coefficient deals with molarity. Okay, so 3 successive washings. Now, the primary focus of this chapter is not so much partition coefficients, but chromatography, and that's really what we're going to be talking about for the next 3 classes. What we're going to do today is we're just going to do some overview, and then we'll probably have time to talk about thin layer chromatography. Then in the next 2 classes, we'll talk specifically about GC and HPLC. And there's a lot to be said about both of these things. But let's talk about the basic principles of chromatography before we do any of that. If we're going to do chromatography, and again, if you've taken organic chemistry, you've done at least a little bit of this, plus all of you have done a little bit of it in lab, whether it be through the HPLC lab or through the GC lab. In any of these experiments, you have 2 components. You have a stationary phase, which is usually solid, and you have a mobile phase, which is either liquid or gas. And the whole idea of chromatography is that you have this competition between the stationary phase and the mobile phase. And depending on the polarity of the compounds that you're trying to separate, some of them are going to stay more in the stationary phase, and some of them are going to stay more in the mobile phase. So if you're looking at separating compounds of varying polarities, which you almost always can do, then this is a really useful technique to do it. So what we're going to talk about is some of the terminology and some of the basic techniques that are used for this, and then we'll put this to more specific terms in GC and HPLC. All right, so first of all, most chromatography would be qualified as adsorption chromatography. In other words, what happens is the molecules that you're trying to separate are adsorbed on the surface of the stationary phase. As the mobile phase passes over that, the molecules dissolve into the mobile phase and then are reabsorbed onto the surface of the stationary phase. And so if you want molecules to stick to the stationary phase, you need a stationary phase that has similar polarity to your molecules, or at least similar polar properties to the molecules you're trying to separate. Okay, and so again, the whole idea is you have this competition, and really this is how all chromatography works. But the bulk of chromatography that's used in organic chemistry would be classified as adsorption chromatography. The compound is adsorbed onto the stationary phase. Now, why does this happen? What causes adsorption? Why would a molecule be attracted to another molecule? Think back to General Chemistry 2, Chapter 11. What was the topic in that chapter? That's probably not a fair question. What was covered at the beginning of General Chemistry 2? What keeps substances together? What are those forces known as in very general terms? In other words, if I look at this solid, this tabletop, it's made of plastic. What holds the molecules that make up that plastic together? Ah, yes, okay, intermolecular forces. And what are the three intermolecular forces that you're looking at? Yeah, okay, you have dispersion forces. Actually, dipole-dipole is also considered a van der Waals force. But so the van der Waals forces, which are the weaker of the two, are first dispersion and second dipole-dipole interactions. And that's essentially what you're taking advantage of when you look at adsorption chromatography. You can have a stationary phase that has a dipole moment, and it's going to attract molecules that have larger dipole moments to it. Or you can also have a stationary phase that doesn't have a dipole moment. And the way chromatographers often describe this is greasy versus polar, or I should say the other way around, polar versus greasy. Something that has dipole moment is polar. Something that is nonpolar is often referred to as being greasy, because it behaves like grease. What happens when you try to dissolve grease in water? Nobody's ever done it? Yeah, it doesn't happen, right? That's why you have to use detergents and such like that to clean your clothes. Otherwise, the dirt that you pick up, which is often greasy, doesn't get dissolved. Okay, you're doing something to make the water less polar, or more likely the grease more polar. And you can read about soap technology somewhere else. Okay, if you have a mobile phase that is too close to your stationary phase, then you don't get the competition you need to separate your mixture. And some of you might have seen this with the HPLC lab. If you played with that simulator and you made the mobile phase as non-polar as you possibly can get it, then all of the components of your mixture come out at once, because they don't stick to the stationary phase as well. So again, in order to enact a good separation, what you have to do is you have to set up some kind of competition between the mobile phase and the stationary phase. And sometimes that takes more work than others. All right, so we have two types of adsorption chromatography. If you do column chromatography in a typical organic chemistry lab, you're doing what's called normal phase chromatography. And in that particular case, your stationary phase is very polar. The most common stationary phase that's used for normal phase chromatography is silica gel, or silicon dioxide. It's very polar. And you use a mobile phase that tends to be fairly nonpolar, because as you increase the polarity of your mobile phase, the stationary or the compounds you're trying to separate tend not to stick to the stationary phase very well. On the other hand, you can also have, and this is how most HPLC is set up, you have what's called reverse phase chromatography, where your stationary phase is very nonpolar. It's very greasy. And your mobile phase tends to be polar. You notice with HPLC, one of the solvents that's used for the mobile phase is just water. The other common HPLC solvents are methanol and acetonitrile, both of which are fairly polar and also miscible with water. Okay, so that's the first thing you want to be aware of. Normal phase is used for a lot of benchtop column chromatography. Reverse phase is used almost exclusively for HPLC. There are some normal phase applications of HPLC, but they're not very common. You know, if you just go into a typical chemistry lab that has an HPLC in it, like ours, it's going to have a reverse phase column on it because that has the most use as far as chemists are concerned. Okay, so let's look at some examples. We used to do this in this course many years ago. We used to, actually I had the students do some synthesis. You can buy ferrocene. It's a bright orange compound, and it's a really bizarre compound in many ways. What it is you have two cyclopentadienide anions, okay? C5H5 with a minus charge on it. Now, what compound is that similar to? Benzene, exactly. You have exactly the same setup as you do in benzene. You have a delocalized pi system with 6 electrons in it. It's aromatic. And so the cyclopentadienide rings tend to be, or they show aromatic behavior. You take these things and you sandwich them around an iron 2, and really what happens is they do physically sandwich the iron 2. It's kind of deceptive the way it's drawn here on this slide. You have 2 rings that are both parallel to each other with an iron 2 atom right in the middle of it, or an iron 2 ion right in the middle of it. It's a very stable compound, and one of the things that you can do with it is you can do a lot of the same chemistry that you can on benzene, but it's a lot less hazardous and it's a lot easier to handle because ferrocene is a solid as opposed to a liquid. And so one of the things you could do, and actually I did this is when I took organic chemistry as an undergraduate, is we used ferrocene as a starting material for Friedel-Crafts acylation. And so what you do is you take ferrocene, you mix it with acetic anhydride and phosphoric acid, which is one of the ways you can do Friedel-Crafts, and you acylate the ferrocene. However, it's not clean. You acylate once, you acylate twice. And so whenever you run this reaction, what happens is you get all 3 of these compounds in the crude product from the reaction. It's not a clean reaction. The nice thing about this is that these are different colored. This one is kind of a bright orange. This one is kind of a red orange. And this one is yellow. And so you can use chromatography really easily to separate these things because you can see the bands move down the column. So let's ask ourselves a question. If we're going to do normal phase chromatography on this crude reaction mixture, which of these 3 compounds is going to be the most polar? Yeah. Why is that the most polar? Simple reasons. More oxygens. That's the easiest answer to this. You have a lot of oxygens in a compound, that compound is going to be more polar. Okay, there's no hydrogen bonding in these compounds, but the compound with more oxygen is going to be the most polar. The compound with no oxygens is going to be the least polar. In fact, ferrocene is basically greasier by these standards. It actually does have somewhat of a dipole moment because of the aromatic system, the same way as benzene does. So, if I were to use a normal phase setup to separate these three components by chromatography, which of these three is going to stick to my normal phase column the most? Yeah, okay. So if I was using silicon dioxide, let's see if I can do this cleverly with different colors. If I use silicon dioxide as my column material, or another one that's often used is alumina. If I use something like that, these are considered highly polar, and so what I'm going to see is that the diacetylferrocene is going to stick the most. And so if I try to run a column with this using, say, a nonpolar solvent, then the diacetylferrocene is going to come out last. And one of the problems that you might have in this kind of situation, and I remember seeing this as well, is you have to be careful to pick a mobile phase that's polar enough so that you move all three of these things through, but not so polar that you move, or yeah, not so polar that everything moves through at once. How do you do this? Yeah, you can change the composition of your mobile phase as you go along. Okay? Think about this. If you've done column chromatography, I know you've done a little bit, Manny, you typically use hexane's ethyl acetate as a solvent mixture to run through your column. In other words, that's your mobile phase. And what you can do is you can vary the polarity of your mobile phase simply by adding more ethyl acetate to the mixture, increasing the percentage of ethyl acetate. And one of the ways you can separate these three compounds from one another is you could start a column with about 20 or 30% ethyl acetate, and then you'll elute off the ferrocene fairly quickly. You'll elute off the acetylferrocene also fairly quickly. But then to get the diacetylferrocene off, you have to increase the concentration of ethyl acetate. Otherwise, you're going to be there all day. And so you kick it up to about 40 or 50%, and the diacetylferrocene comes through, because that competition becomes less as I increase the polarity of the solvent. Now, let's think about it in HPLC terms. If I run this mixture on an HPLC, which is possible, I'm going to use what's called a C18 column. Let's use a different color for this. Let's do green. A C18 column, okay? And essentially what that means, the actual basis of the column is very similar. It's usually particles of silica, but they're coated with a compound that has these 18 carbon chains dangling out of it. And as a result, the actual surface of the column is very greasy. It's very nonpolar. And so if you were to use that system, then what you would find is that these three compounds would elute from my column in reverse order. In other words, the diacetylferrocene would come out first, the acetylferrocene would again come out in the middle, and the ferrocene would come out the last, because it's going to stick the most to my stationary phase. So in a C18 column, you would see this come through. Now, what's interesting about this is that reverse phase chromatography is not often used on the benchtop other than for HPLC. You can find applications of reverse phase chromatography that aren't HPLC, but they're few and far between, and one of the reasons is that it's very expensive. Okay. if you think about normal column chromatography, do you ever recycle the materials that you use in that? Did you do, I'm trying to remember, did you do normal column chromatography in organic chemistry at all? Okay, yeah, I was wondering about that. It takes a long time. That's part of the problem. It also is expensive because the materials are expensive. But if you run a normal column, when you're done, you get rid of the silica gel. You don't reuse it. Whereas an HPLC column, which is reverse phase, costs 50 times as much, but it gets reused. Okay, now there's what silica looks like. Silica is not just SiO2. What it is it's a covalent network solid, which is something else that was discussed in that first chapter of General Chemistry 2. You have a network of silicon dioxide molecules. All right, really what it is it's a single molecule that has the empirical formula SiO2. And it looks something like this. You have silicon oxygen single bonds throughout. And so the network becomes, it can be thousands and thousands of these formula units in series. But because of the oxygens, the silicon dioxide is very polar. Okay. So this is the idea again. If we use something if we use a mobile phase on a polar stationary phase that is not very polar, then what's going to happen is my components are going to tend to want to stick to the stationary phase and not move through. If I increase the polarity of my mobile phase, then I can start to set up this competition. But if I increase the polarity too much, then everything just comes through at once. How do organic chemists figure out what works the best for this kind of thing? Do you typically do a reaction and then just run a column, or do you do something first? This is something I know if you took Organic 2 that you probably did. Thin layer chromatography, we'll talk about it more in a few minutes. Oftentimes what organic chemists do is they use thin layer chromatography as a way to help them decide, okay, if I'm running normal phase chromatography, what solvent mixture is going to give me the best separation of the different components of my reaction mixture? And then it also is used as a way of determining if the fractions that come off of a column are clean. Take a fraction, you spot a TLC plate, and you see, okay, how many spots come through? And do they come through where I would expect them to, given the nature of my compound? All right, so here's a list of common solvents in order of increasing polarity. So you start out with really short hydrocarbons. Okay, hexane is a little bit more polar because it's longer. Carbon tetrachloride, toluene, benzene, dichloromethane. Then we get into the chlorinated compounds. Then diethyl ether, ethyl acetate is fairly polar. Once you get down here, the 4 compounds at the bottom of this list are miscible. In other words, the polarities of acetone, ethanol, methanol, and water are similar enough that you can actually mix them together infinitely. Okay, you can't do that with ethyl acetate. You can get some ethyl acetate to go into aqueous solution, but not a whole lot. And then, of course, that gets worse and worse as you go up this list. And the same is true, you can kind of separate these out. If I tried to mix chloroform with hexanes, I might not have such good luck. If I tried to mix chloroform with water, I'd have terrible luck. On the other hand, if I tried to mix chloroform with ethanol, it might work. right? And that's another thing you have to think about. If you're going to make a mobile phase that is variable constant or composition, you need to have compounds that will mix with each other. And hexanes, ethyl acetate is about as far apart from each other as you can get for that kind of thing to happen. And so that's one of the most common mobile phases that's used for normal phase chromatography, on top of the fact that it's fairly cheap and fairly non-toxic. Those are other things that are desirable. How do you make ethyl acetate? How do you make a typical ester? Yes, acetic acid and ethanol. Okay, you mix the two together, you run an esterification reaction. Why do I bring that up? Because if you buy alcoholic beverages like wine, it can happen in the wine itself. There are circumstances, you know, the whole fermentation cycle. You start out with sugar, the sugar ferments to alcohol, but if you have the wrong organisms in your fermentation mixture, it will continue to ferment to acetic acid. As a result, if you have acetic acid and you have ethanol in the same solution, that solution is acidic, you get ethyl acetate in there. And what happens? I hope nobody's tasted ethyl acetate, but you know what the smell is like. It smells very solventy. You can get alcoholic beverages that are very solventy in flavor because they have ethyl acetate in them. All right, it's considered a flaw. If you're a taster, I learned years ago how to judge beer, and this is one of the major character flaws in a homemade beer, is if you taste the beer and it tastes like solvent, you know that something like this happened. Not good, not good. Not ethyl acetate. Some of the other ones, yeah. I mean, you make amyl acetate like you did in lab. That's banana, right? Yeah. Yeah, there's the Tutti Frutti. I forget what that one is. There's cherry. There are a whole bunch of them that are higher. But again, the way those work, your threshold for those compounds in terms of your taste and smell is very low. They put those compounds in very, or they occur naturally, or they're placed in the products at very low concentrations because they don't need to be very high. If you put them in at high concentration, either one of two things happens. You stop tasting the compound, or it starts to taste nasty. So that's another part of taste. You find these compounds that have desirable flavor characteristics, but only at certain levels. Okay, and one of the ones that I think of the most is this one. I'm digressing a little bit, but called dimethyl sulfide. All right, this is common in beer, and in low levels it's desirable, but when it gets up above a certain level, it starts to taste like cooked corn, or even just sulfury. But in very low levels, it's considered desirable, especially in lager beers, because that's where it occurs the most. You drink a bottle of Corona or any other Pilsner from anywhere in the world, you're going to taste a little bit of that dimethyl sulfide. Okay, so in thin layer chromatography, and actually I've got more slides about this later on, but this is useful to see. What do you do in a typical thin layer chromatography experiment? You take a plate, all right, whether the plate is glass backed or plastic backed. Doesn't really matter. But you take this plate, and what do you do with it? It's coated with your stationary phase. It's coated with a very thin layer of your stationary phase. We've got tons of these in the back. And I think most of you have seen them if you've been in an organic chemistry lab. What you do is you take a pencil or something like that, and you put a mark down at the bottom of the plate. Then you take your compound, or your crude mixture rather, and you spot the plate on that mark. Okay? You take your TLC plate and you place it into a little container with a small amount of mobile phase on the bottom. And of course, the idea is to vary the composition of the mobile phase. So say, for example, we do this here, and after we've allowed the solvent to elute up the plate, and the way this works is the solvent moves up the plate by capillary action. It defies gravity and it moves up, and then when you're done, you stop and you mark where the solvent went to, and you see different components that have separated along the way. Something like this. Now, one of the things you can do with this, first of all, what you want to say is, all right, if this purple dot represents one compound and the green dot represents something else, then it looks like I've got pretty good separation here. But I also have to calculate what's called an RF value. It's a retention factor or something along those lines. And essentially what you do is you do this by measuring. You measure the distance that the solvent traveled, which would be here, versus the distance that the spot traveled. And you divide the distance that the spot traveled by the distance of the solvent front, and you get an RF value. That's why you learn to calculate these things in organic chemistry lab. Did you calculate RF values in organic chemistry lab? Yeah, okay. All right, so why do you do this? That's the question. And I remember in organic chemistry lab, I learned how to do it, but I didn't know why. What's the point? Here's the point. If you're going to run a column with that same solvent mixture, the RF value will give you some idea about how much solvent you're going to have to push through that column before the spot comes through. And so say, for example, you have a compound that you find has an RF of 0.80. What you can say then is, all right, if the RF value is 0.80, how many column volumes am I going to have? It's 1 over 0.8, which is, what about 1? Okay, 1.25. That's not bad. All right, so that means if you have a column that has a volume of 50 milliliters, you're going to have to push about 65 milliliters of solvent through before your compound comes through the column. On the other hand, what if you have an RF of 0.2? Then your column volume is going to be 5. And so that means if you had a 50 milliliter column, it would take 250 milliliters of solvent to push that particular compound through. And so what do? You increase the polarity of your mobile phase. So it takes fewer column volumes to do. And oftentimes what would happen, and this was actually my first job in industry. I got hired, it was almost 20 years ago now, by a company down in Princeton. And what they were looking to do was, okay, if an organic chemist makes a reaction mixture runs a series of TLC plates, could I develop some kind of flash chromatography method that would allow the chemist to basically to bring their reaction mixture into the lab where the chromatography setup was, plug in a number of parameters, punch a button, walk away, and come back in 20 minutes and have fractions come off the column that they could use that were pure. And it worked. It worked really well. Essentially what I did was I wrote a manual saying, okay, you run TLC plates, you vary your composition. You could start with a certain composition to force your less polar column or compounds through the column. Then you can kick up the polarity to a higher level, and you could vary this based on your TLC, and force the more polar compounds to come through in a fairly rapid time period. It was really nice. And I was surprised at how well it worked. And I learned a lot about chromatography doing that. Plus I got paid very well. So it was nice. And then they hired me back the next summer to do the same sort of thing using an HPLC. To do an analytical method, which is the kind of chromatography we're doing, and then match that to a preparatory method where you could separate 500 milligrams of a crude reaction mixture into its components in a matter of about 10 minutes. Okay, so our primary discussion for this section of the course is going to be adsorption chromatography. I want to bring up a couple of other types of chromatography at the very beginning because you might see these later on in your chemistry education. Dr. Yarmchuk said that I need to include this. We did have at one point the ability to do size exclusion chromatography. The idea behind size exclusion chromatography is that instead of your stationary phase being non-selective, you choose a stationary phase that has holes of a very specific size. And the idea is that the molecules that you're trying to separate out from your mixture have a similar size to the holes that appear in the stationary phase. Now, why would we do this? We do this because this gives us a way of separating things like proteins. And that was the lab that Dr. Yarmchuk actually developed with size exclusion chromatography. Somewhere in our lab, we still have a size exclusion column. And what he did was he developed a lab where the students would run a buffer through the HPLC with a protein mixture. And the idea was to separate the different components of the protein mixture out. And so biologists do this. And this is often, I think, also how a lot of monoclonal drugs are separated from one another because they're large molecules. Okay, the class of compounds that we use for this kind of things are called zeolites. They're silicas. They're not pure silicon dioxide. They usually have other things in them like aluminum or sodium and things like that. But the way they crystallize, you've got some kind of network with a large hole in the middle of it. And you can kind of see it from this picture. I should try to find a color representation of this instead. All right, you have to think kind of in 3 dimensions. Essentially, you have this sphere of silica around a hole in the middle. And depending on the composition of the silica, you can vary the size of the hole, and therefore vary the size of molecule that will get adsorbed into the stationary phase. Okay, this was another diagram from the same book using the same idea. Okay, so you have 3 different compositions, 3 different hole sizes, and actually hole shapes as well. So size exclusion chromatography, it's got a niche. especially if you're doing protein chemistry of any sort, which I would say is probably one of the hotter areas of chemistry. If you want to go and work in industry now, it's something to consider, because there are jobs for large molecule chemists, a lot more jobs for large molecule chemists than there are for small molecule chemists at the moment. I'd love to see that change. Okay. One of the other things I wanted to talk about here, and actually I developed a lab where we use this, although we don't have anything that works really well with this, is this idea of ion exchange chromatography. This is really important for purification of water. All right, so why would you do this? Well, say for example, and this is how I learned about it as well. I was an undergraduate. I was making chromium complexes. And I was looking at ways to separate these chromium complexes from one another. They had a charge. They were all cationic. And so the professor I was working with said, okay, let's get some ion exchange resin, and you can run some ion exchange chromatography to try to separate the different ions that you've made. Nice idea, okay? And so it's real simple. Classic ion exchange chromatography works like this. You've got a resin with a surface that has a bunch of OH groups. And the way this resin is set up, these hydrogens are acidic. And so if you place the right ion in, or if you run the right ion across this surface, what happens is the ion replaces the proton on the surface. And then if you increase the acidity of your mobile phase, you can actually force this ion back off this surface and into your mobile phase. That's the idea of ion exchange. It works very well. Now you can also do this with anions. You have anion exchange resin where instead of having an acidic proton, what you have is a hydroxyl group on the surface of your ion exchange resin that will come off easily, and it will exchange with anions. Now where is this used most commonly is next door. How many gallons of deionized water have we gone through this semester? Or you could even look further back and say, since you've been here at Middlesex, how many gallons of deionized water have we used? Lots. We go through hundreds of gallons of deionized water in a month. And rather than buy this stuff, which is really expensive, it's a lot cheaper to make it on site. And you may have noticed this when you go back into that prep room and to get your volumetric flasks or ice. On this side against the wall, there are two what look like gas tanks. They're cylinders. They're about so wide and about 1.5 meters high. Those are ion exchange beds. And so what you do is you take tap water and you pass it first through an acid ion exchange bed. And what happens is all the cations in that tap water exchange for hydrogen ions from the cation exchange resin. Then you pass the same water over anion exchange resin. Now all the anions that are left will exchange with hydroxide ion. And so the net result is you're going to replace whatever salts you have in there with water. Hydrogen ion from the cation exchange, hydroxide ion from the anion exchange. Since there's charge balance, you should get water out. And it works. That's how we make all the deionized water that you use. It's a, yeah. Oh, much, yeah.
But so why like on ShopRite you see only distilled water?
Ah, okay. That's a really good question. Why? There are some applications where deionized water is not enough. What's the problem? think of it this way. What are the normal contaminants in tap water? Okay, you'll have ionic contaminants. You have, say sodium chloride. You have iron salts. You have copper salts, chromium salts. And really, in some areas, like unfortunately Newark, you have lead salts as well. Okay, this kind of chromatography is going to get rid of all that. But the problem is you also have organics in that tap water. Okay, for example, if you chlorinate tap water, which we do to kill off organisms, one of the byproducts of chlorination is chloroform. There are very low levels of chloroform typically in tap water as a result of the chlorination. Low enough, at least it's thought, that everything is okay, because chloroform is actually considered to be a carcinogen, but it's still there. So what if you have an application where you don't want chloroform in your water? You can't use our deionized water for that application because it's still going to be there. And so how do you clean that water up? You distill it. The difference is, though, the cost. I mean, think about, first of all, how much energy goes into vaporizing water and then condensing it back down. It's a huge amount of energy because water has a very high heat capacity. So distillation, though it's a viable way of doing things, is much more expensive than deionization. And on a cost basis, especially if we go through hundreds of gallons of water, deionization is a much more effective way of doing things. And it doesn't, well, part of the reason it doesn't affect things in our lab is because we deliberately choose to do things that don't involve organics so much. But it is a good point. There are definitely applications where you want to use distilled water. What's another way of cleaning up water? This has come into vogue very much in the last 20 years. Goes back to something else you learned back at the beginning of general chemistry too. You can do reverse osmosis. There are places in the world, okay? My wife grew up in Santa Barbara, California. Santa Barbara has had water problems for about 25 years. And so the thought was, and there are other communities in California that are in similar situation. You're down on the coast, you don't get much rain, and you need water. The town needs tap water. So what do? Well, you can draw water from the water system that's already stretched to its limits, or you can take something that's plentiful and purify it. And so what a lot of California coastal communities do, and a lot of places elsewhere in the world where the climate is arid and you're right next to the ocean or a sea, you take that ocean or sea water and you reverse osmose it. What is osmosis again? What's the idea? Yeah, exactly. If you have a semi-permeable membrane and you have on one side pure water and on the other side you have a solution. Under normal circumstances, there's pressure for the pure water to move into the solution through this semi-permeable membrane. Now, the pores in this membrane are small enough to allow water molecules through, but not other solute molecules or ions. And there's pressure because the concentrations on either side of this membrane want to equalize. It's kind of like the galvanic cells I showed you where we had a concentration difference from anode to cathode. It's the same idea. There's pressure to equalize the concentrations on either side of the salt bridge. It's essentially the same principle. Okay, so if you do reverse osmosis, what you do is you take water with solutes in it, put that water into a container with a semi-permeable membrane, and then put a huge amount of pressure on it to force the pure water through the membrane, leaving behind the solute molecules and ions. I forget, I mean, you can calculate this. For seawater, the molarity is somewhere around 5. And so you can figure out the osmotic pressure for this. It's an order of hundreds of atmospheres. And so engineering this is not an easy thing to do. But engineers have come up with a way to do this. And usually it's done stepwise instead of all at once. So you reduce the amount of pressure that you're putting on things. And there are other ways of doing this. You can actually buy RO purifiers for your home water system. They're not that expensive. You can get a good one for around $100. And it's another way of cleaning up your water. It's definitely less expensive than distillation. And really, it is an application of chemical separations. You're just pushing back across a semi-permeable membrane. And so, I think this technology was developed in Israel because around the Dead Sea, there's really no water to be had any other way. But it's used in a lot of places now. I know they use it in Brazil as well, in some of the communities that are on the ocean. Okay. What was the other one I was going to show you? We have size exclusion, we have ion exchange. It's gone. Sorry, that's the way my brain is functioning these days. I had one other thing I wanted to talk about as far as separations are concerned. It'll probably come back to me. Let's spend a little bit more time with thin layer chromatography. These are some slides that Dr. Yarmchuk put together on thin layer chromatography and open column chromatography. I'm going to cherry pick them, but there are some things in here that are useful. So if you want to take a look at them, please feel free. Also, again, I would recommend you spend some time with the chapter in the book. And it's chapter, I think it's 24, 25. But I'll make sure I post it on Canvas with the homework. There's not going to be a whole lot of homework this week either, but I'll make sure that you have 2 weeks to do the assignment, because you're probably going to devote most of the next week to doing or to getting ready for the exam, right? Okay, so thin layer chromatography. You've got a stationary phase that's very thin. It's usually on glass or plastic, occasionally metal. The most common type of chromatography done with TLC, as it's called, is just normal phase using silica as your stationary phase. Okay, occasionally alumina, occasionally also paper is used, or cellulose, because that cellulose would also fall into the category of normal phase chromatography. How do you make these things? Well, you typically spread an aqueous slurry of your stationary phase on a layer. And back in the bad old days, they were made by hand. You can tell that Dr. Yarmchuk came from that time period because he knew how to make TLC plates from scratch. I come from the era when it was easy to buy these things, and we still live in that era. Why spend hours and hours in the lab making these things when you can go out and spend $40 on a good set of pre-made ones instead? We have hundreds of boxes of these things. Lots and lots of plastic-backed ones, which for some reason most of the organic chemists on this campus shy away from. They work just fine for most applications, but for some reason people shy away from them. They prefer the glass-backed ones, which are much more expensive. Okay, one of the keys is silica gel does readily absorb water. And so one of the things that you typically do with these things is you either keep them in a dry environment or you put them in an oven to drive the water off, because the water can interfere with the chromatography you're trying to do, depending on the circumstances. Okay, there are reverse phase TLC plates. I believe we have some of these things. One of the most common stationary phases for reverse phase is something that's referred to as fluorosil. It's a fluorinated silicon dioxide. It's not truly greasy, but it is greasy, or it's greasier than regular silica. But you can also take silica gel and coat it with greasy hydrocarbons, C18 or C8. And these are things that we use for HPLC. Okay. So why are we doing this? Again, we want to do it because, in most cases, we want to do it because it gives us the ability to develop chromatography or column chromatography conditions. Okay. Follow reactions. You can actually do prep TLC as well. We have the ability to do that. I can't remember. Did you do any of that, Manny?
Yeah.
Where you took a large plate and you ran the TLC and then you scraped off the bands that you wanted and dissolved your solute away from the mobile or from the stationary phase. Yeah, okay, so it's still used. Okay, so there's the basic technique. Again, if you've done this in lab, you know how to do it. You use a capillary to spot the plate. You put it into a chamber with solvent and you let it develop vertically by capillary action. Okay, and it looks something like this. This is a classic prep tank. You have a big tank, you put a little bit of solvent in the bottom. The more common tanks that we have are just cylindrical, something like this. They look like a beaker and they have a lid on the top of them, or a beaker without a spout on them. Back when I first came here, we didn't even have any of those kinds of reservoirs, so I developed a bunch using just glass bottles, wide mouth glass bottles. They work just fine. Okay, blah, 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 blah. Spotting, okay. Lots of information about that. Developing, blah, 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 blah. Okay. How do you visualize what happened in a TLC plate? If you're using colored compounds like the ferrocene, this is easy. You just look for the colored spots. But most organic compounds don't have much color associated with them. So how do you visualize? What'd you do? Yeah. Okay. You use a stationary phase that has some kind of luminescent dye on it. And so what you can do is when you finish running your TLC, you can shine a UV light on that luminescent dye, and where there is other compound, it interferes with that luminescence and you see these dark spots. It's a really nice way of doing things. What's another way? There are two other ways that are commonly used. One is you can take your TLC plate and place it into iodine vapor. You just take a jar of iodine crystals and you put your TLC plate in there for about 30 seconds, shake the thing around, the iodine vapor gets absorbed onto the surface of the TLC plate, and again, you can see where your spots are by that, because the iodine the iodine is kind of brownish. There's a third way that I haven't seen for over 20 years, and that is you can use ammonium molybdate solution. You can take your TLC plate and just dip it in there, and it turns your TLC plate green except where there are spots. And I knew some people when I was a postdoc in North Carolina that insisted that that was the best way to visualize what was going on in a TLC plate because it was so clear. Okay, so blah, blah, blah. There. Okay, another one you can spray with sulfuric acid. I've never seen that one. It tends to char some organic compounds. Okay, and there are other reagents you can use, but ammonium molybdate is a good one for that. Okay, actually, here's some other ones. Fluorescein, ninhydrin, DNP, which I'm not sure what that is for. Antimony chlorides, nasty. Bromophenol blue, and diphenyl carbazide, which is also nasty. Okay. We've already talked about strength of solvents. Okay, we've talked about RF values. One of the things that you definitely want to be prepared for in the coming exam is how to measure and calculate RF values. It's really simple. Okay, and of course, in order for you to do it, you're going to have a ruler. All right, so if you want to measure an RF value, you simply measure the distance from the spot line to the solvent front, and then the distance from the spot line to the spot. And actually, he's got this vertically now. So here's one distance. Here's the other one. And the RF is just the dr divided by dm is in his notation. All right, very simple. And the way he has it here is you measure to the center of the spot, not to the head of the spot. That depends on who you talk to. But in terms of determining column volumes, measuring to the center of the spot is probably the most useful. Okay. I think that's pretty much all I need to say about this. What should we do with the remainder of our time today? We have about half hour left. What should we do? You want to go home? You want to do some problems on that review sheet? Yeah, I think that makes the most sense, doesn't it? All right. And then we'll start GC next time. We'll do GC in 2 weeks, and then we'll do HPLC in 3 weeks, and we'll be done. Oh, and I'm tired. Sorry, I'm really tired. It's been a long week, hasn't it? Okay, so if you want to look at this first problem, you certainly can, and I'll work it on whenever I get the key out for this thing, I will work it, but it's not really necessary for this coming exam. It's another application of a redox titration, and you have essentially two components to it. It might be worth looking at, but I think our time would be better spent on some of the things that we've covered more recently. What about something like this? What are we going to do? This is a strange problem because most problems of this type in this day and age are not going to appear this way. How do I change percent transmittance to absorbance? That's one of the things that I have to think about here. What's the equation that relates the two? Yes. Absorbance is equal to the log of 100, which is 2, minus the base 10 log of your percent T. That's an equation that's worth remembering. All right, and of course, if you go in the other direction, you can rearrange it. Now, why would something like this be reported with percent transmittances? Yes. All right, up until very recently, instruments were designed only to measure percent transmittances much more accurately than they measured absorbances. We still, somewhere in the bowels of this building, have some analog spectrophotometers. Okay, so one of the things that we have to do in this problem is we have to change our percent transmittance values to absorbance. So, for example, if we look at this first one, our solution has a concentration of 0.05 milligrams per liter of our analyte and 79% transmittance. Notice also how the concentration, as the concentration increases, the percent transmittance goes down, okay? The relationship you're looking for is Beer's law, which is there's a direct proportionality between absorbance and concentration. So somehow we have to change percent transmittance to absorbance. All right, so if I take 2 minus the log of 79, what do I get? Okay, so the first absorbance is 0.103. Okay, and we can go down with that. What's the easiest way to do this? Yeah. Why not set up an Excel spreadsheet? If this particular value was in cell B3, for example, you could say in C4, or actually in C3 or D3, you could type the function equals 2 minus log 10. Don't forget that 10, because if you just use log in Excel, actually I can't remember. Yeah, you want to double check it, because in some of these programs, if you just use log, it's natural log. But I think you're right. I think Excel, it works fine. And I think natural log is actually ln. Open parentheses, B3. And then you copy that down. And again, this number will change for each one. You can just get the absorbance that way. All right, now what else do we have to do with this problem? Okay, what do we want to plot on that graph? This is Buckminster-Fullerene. By the way, what is Buckminster-Fullerene? Okay. It's not only a compound. Technically, it's an allotrope of carbon, because Buckminster-Fullerene is pure carbon. Okay, what are the common allotropes of carbon? Diamond and graphite. Okay, but there are a whole bunch of other ones as well. You know, there's all this carbon fiber technology that's out, that's used extensively for autos and for aircraft and for bicycles. Okay, Buckminster-Fullerene was discovered sometime in the 80s. It looks like a soccer ball. It's a single molecule with 60 carbon atoms in it. It was discovered, or at least I shouldn't really say it was discovered. It was characterized by a gentleman, or by his name was Smalley, at Rice University in Houston. Very nice person. I met him a couple of times when I was a graduate student. He's now deceased. One of the coolest things, though, was that when I was a grad student, there was a guy in my group who said, I can get the crystal structure of Buckminster-Fullerene. And he did. Somebody had tried just to grow crystals of regular Buckminster-Fullerene, but because of its symmetry, you could, even though you could grow crystals of it very nicely, the way the ball of carbon atoms oriented itself in the crystal was highly variable. And so you couldn't see the positions of individual carbon atoms very clearly. In other words, the crystal was disordered. This friend of mine had this brilliant idea: let's bind it to a transition metal and then get the crystal structure. And he got it. Basically made his name as a chemist. And one of the things that I'm really pleased about is when he talked about this, when he finished his degree, he thanked me because I taught him how to do synthesis. Okay, so this is C60. When you dissolve C60 into benzene, or toluene, it's this very brilliant purple color. It has a very, and it's got a very high absorptivity. Okay. So one of the other things you're going to have to do with this is you're going to have to calculate the molarities of the solutions. You're given the concentrations in milligrams per milliliter. How do you do this? How do you change milligrams per milliliter into molarities, moles per liter? Okay, that's going to give you millimoles per milliliter. Then what? If I multiply by 1,000, that's going to give me moles per milliliter. Or actually, what will it give me? Is it millimoles per milliliter? Well, let's think about this for a second. If I multiply this by 1,000, what do I get? I get grams, or actually milligrams per milliliter is the same as grams per liter, isn't it? So you're right. If we just divide by the molar mass. What's the molar mass of C60? Yep. All right. 12.01 times 60. You do that, and let's see, what did I get? 720.
720.66.
Yeah. So what you could do to get your molarities is you could take the contents of these cells. Say, for example, this is in cell A3. You could say, all right, I'm going to calculate the molarity by saying equals A3 divided by 720.66. And then copy that down. Except I wrote it wrong, didn't I? How do you do this in Excel? Does it look this way? Isn't it like this? That slash is your division sign. So you can get your molarity. So what I would do is I would set up column C as a way of calculating the molarity. Column D as a way of calculating your absorbance. That way you're set up for a chart. Okay? What do you have to put in that chart? What goes on the y-axis? What goes on the x-axis? Yep. Okay. So your molarity of C60 is going to go on your x-axis, and your absorbance is on your y-axis. And the beauty of doing this is, by default, if you highlight two columns of Excel data, Excel will put the first column on the x-axis. And so that's one of the things you always want to think ahead, try to think ahead about when you set these things up, is where are you going to put your X data and where are you going to put your Y data? Because it's a lot easier to do that than to go back and say, okay, I want to flip my axes. You can do it in Excel. It's not that difficult, but it's a lot easier just to set everything up ahead of time so that it's correct. So you put your molarities first, your absorbance second. The absorbance is going to go on the Y-axis, and the molarity is going to go on the X-axis. How do I know if this data obeys Beer's law? Okay. Yeah. If my data obeys Beer's law, I should get 4 points, or how many points are there in here? Is it 4 or 5? It's 5. Okay, I should get 5 points in a straight line. Let's put a 5th point in there just for the fun of it. Okay, and again, as you say, if you look at that, you try to draw your trend line. Do you want to force this trend line through 0, 0? Yeah, in ideal circumstances, try it. What's been interesting, though, is everybody's data that I've seen this semester, whether it's from you guys or from my other class, the Gen Chem 2 lab I have on Wednesday morning, forcing the Beer's law data through the origin skews it. I don't understand what's going on there. It has something to do with how the blank is measured, I think. I haven't seen anybody's iron solutions yet. Okay, I haven't had a chance to look at those labs. I'm hoping I have some time over the next week to do that. But again, I can make no guarantees. But that's something in theory, if something does obey Beer's law, then if the concentration is 0 molar or 0 parts per million, the absorbance should be 0. And that's what the blank is supposed to do for you. So, that's a question here. Does this obey Beer's law? And then the last thing you can do is if it does obey Beer's law, you can calculate the concentration of Buckminster fullerene in a solution whose percent transmittance was measured to be 50. What is the absorbance equal if a solution has a percent T of 50? Yeah. Now, another question you want to ask, and I think it's going to work, is does that 0.301 absorbance fit in the range of absorbances that you get here? Because one of the things that you have, and I think I mentioned this before, if you're going to do a Beer's law study and then you're going to measure the absorbance of an unknown, if I do my Beer's law study and I get 5 points, and then my unknown has an absorbance somewhere up here, there's no guarantee that the Beer's law relationship is going to extend up to that line unless I have made measurements. And so what I would do ideally is take this and dilute it by 1/2 so that the absorbance of the solution now is within the range of the points that I collected from known solutions. If that's not the case, then I have to do something like dilution to get it that way. And the other thing you want to think about is again, if you're going to work on an independent project where you're dealing with Beer's law, you want to make sure that all the solutions you use come in with absorbances of less than 1. Now that's definitely true here, because if absorbance is 1, then percent transmittance is going to be 10. Okay, so see what you can do with that. I'll try to set up a spreadsheet at some point myself, and you can compare what you did with this. All right, easy stuff here, right? If I have a photon with a wavelength of 412 nanometers, how do I calculate the frequency? Three things you want to remember for this. The first one is that the frequency times the wavelength is going to give you the speed of light. And the speed of light is 3 times 10 to the 8th meters per second in a vacuum. Okay, that'll help you with the first part. For some of the other things, what else do we have to remember in here? We have to remember that the energy of a photon, or of a single photon, is equal to either h times the frequency or h times the speed of light divided by the wavelength. And what is it? 6.626 times 10 to the negative 31 joules times seconds. So, how do we calculate frequency? What do we have to do to the wavelength before we can calculate frequency? Yeah, we need to convert this to meters. So, in this case, the wavelength would be, if you do that, you're going to divide by 10 to the 9th. And if you do that here, you get 4.12 times 10 to the negative 7th meters. Let's not worry about number of wave numbers. Let's just worry about frequency and energy, and then we'll do one other thing with this instead of wave numbers. So, in order to calculate frequency, we simply take our speed of light and we divide by the wavelength in meters. 4.12 times 10 to the negative 7th meters. The units we end up with are reciprocal seconds, which is what we want, which is the same as hertz. So what do we get? About 7.4 times 10 to the 15th? Or 7.4 to the 10 to the 14th? Going to be a high frequency because it's a fairly high energy photon. All right, how do we calculate the energy of a photon? For a single photon, we simply take H, 6.626 times 10. I'm sorry, it's not 10 to the negative 31, it's 10 to the negative 34th. Joules times seconds times 3 times 10 to the 8th meters per second. And we divide that by the wavelength, 4.12 times 10 to the negative 7th meters. Okay. Now, what if we pump a mole of those photons? How much energy do we get? Yeah, we multiply by Avogadro's number. 6.022 times 10 to the 23rd per mole. Yep. 291,000. (291 kilojoules). So if we had a photon of that wavelength, which is in the blue region, you pump a mole of those photons, you're gonna pump 290 kilojoules of energy into your system. Sometimes that's useful. There's an organic chemistry group down in Princeton that does this. My wife was involved with them on the fringes for a while, and actually she worked for a company that the professor set up for a number of years. And their primary way of making compounds is to take a starting material or several starting materials, a catalyst, usually the catalyst is iridium-based, place that all into a container, and then just shine a really intense blue LED on it. And so you're pumping the energy in from the photons that the LED is emitting, and you're generating, and as a result of that, you get a reaction. And actually, I heard this professor speak. His name is McMillan, David McMillan. And he talked about this. A lot of it, he said, was serendipity. You know, they just take things and they throw them in there and see what happens. And they got a lot of really interesting things out of it. All right, so this is very much like what we did last week. We have a solution that contains 1 times 10 to the negative 4th molar silver ion. And it generates a potential of 0.596 volts versus a reference electrode. What is the E for the reference electrode? What do we need to remember? Several things. First of all, let's start at the beginning. Yes, that you'll have in front of you as well. The potential of the cell is going to be equal to the potential, or the half potential of my reference of my silver electrode minus the half potential of the reference electrode. Come on. And so I can rearrange that. My reference electrode has, or can be determined by taking the half potential of my silver electrode and subtracting from it the cell potential. Okay, so how do I determine the half potential of my silver electrode? That's where the 0.799 comes in, right? The half potential of my silver electrode is going to be equal to the half reduction potential at standard conditions for silver. And you want to pay close attention to this, because if you're asked for some other ion, say for example iron, in one of these things, you've got to make sure you pick the right half potential from the standard potentials chart, because there are 3 for iron and there are also 3 for copper. All right, for iron, there's iron 2 to iron metal, there's iron 3 to iron metal, and there's also iron 3 to iron 2. So you have to make sure you know which one you pick. For copper, there's copper 2 to copper metal. We dealt with that one in class. There's also copper 1 to copper metal, and there's copper 2 to copper 1. So the 0.799 volts that we're using here is the half potential for silver ion to silver metal reduction versus standard hydrogen electrode. You can take that minus 0.05916 over N times the log of Q. And for this half reaction, since it's written as a reduction, here's what Q is going to be. Q is going to be equal to 1 over the concentration of silver ion in my cell. So for this specific reaction, we can say EAG is equal to 0.799 minus, N is 1, so I'm just going to write 0.05916 times the log of Q. Now what is Q? Q is going to be 1 over 10 to the negative 4th, which means it's going to have the value 1 times 10 to the positive 4th. And so, what is my half potential for silver? Yeah, it's 1 over 10 to the negative 4th, so it becomes 1 times 10 to the positive 4th. Yep. Does that look familiar? If you've done the calculations for the lab, it's exactly the same. Okay, so I've just given you something. If you haven't done those calculations for the lab, I've just given you something that's helpful for it. All right, because you're in the first setup, your concentration of silver ion is exactly the same. It's 1 × 10⁻⁴ molar. You're measuring that versus a reference electrode, so you're going to do exactly the same thing. Okay, now the voltage you got versus the reference electrode was not this high. All right, so what are we going to do next? We can say, all right, the reference electrode potential is going to be 0.562 volts minus 0.596 volts. So we've got an interesting situation here. We've got a reference electrode with a negative potential. That's possible. It is possible to have that kind of situation. It could mean that the reference electrode has gold in it or something like that. Or it could also mean that the reference electrode has silver in it at a higher concentration. So what is my EREF here?
0.034.
Is it positive or negative?
Negative.
Yes. It's going to be negative 0.034 volts. Okay. Look familiar? So our reference electrode has a potential of negative 0.034 volts. Now what we can do is we can figure out, given the cell potential of 0.213 volts, what is the potential for, or what is the concentration of silver after we've added chloride ion? How do we do that? Well, we still have this equation. If I want to solve for EAG, that's equal to E cell plus my reference electrode potential. Okay, so let's go ahead and do that here. My cell potential is 0.213 volts. My reference electrode has a potential, as we determined in the previous problem, of negative 0.34 volts. What do we get? Okay, 0.179 volts. Okay, so what's next? Yeah, so now we're going to have 0.179, this is the last thing we'll do, equal to 0.799 minus 0.05916 times the log of whatever Q is. And again, Q, remember what Q was from the last example. If we solve for Q, it's the reciprocal of the silver ion concentration. So let's take 0.799 from both sides. So what's 0.179 minus 0.799? Yeah, it's negative point. You said negative 0.332? 632. Okay, so I'm going to multiply this thing through by -1. So I end up with positive 0.632. Oh, 662, sorry. 660? 620? Okay. Sorry. All right. That's equal to 0.05916 times the log of Q. If that's true, we divide both sides by 0.05916. What do we get for the log of Q? $10.48? And so 10.48 is equal to the log of Q. And so 10 raised to the 10.48 power is equal to Q. Or another way of thinking about this is, since Q is the reciprocal of the silver ion concentration, then 10 raised to the negative 10.48 power is equal to the molarity of the silver ion in this solution. What is the molarity of the silver ion? Okay. How do we get the KSP from this? Yeah, okay. So according to what we know, for silver chloride, the KSP is equal to the concentration of silver ion that we measured in our cell times the concentration of chloride ion that we threw in there, which is much, much larger. And so in this particular case, that's going to be equal to 3.31 times 10 to the negative 11th times 0.1. Because that's what the chloride ion is given to us. And so that's going to give us a KSP of 3.31 times 10 to the negative 12th. There you go. Okay. That's a good stopping point. There is more. There's this problem, which involves standard additions. I definitely want to look at that. And then, of course, you've got more problems involving just current, which we did at the very beginning of class. Okay. So we'll stop there. With luck, I'll see you a week from Monday. Okay. And if not, I'll let you know what's happening.